Welcome, everybody. Thanks so much for joining us here today. My name's Julian Wood. I'm a principal developer advocate here with the Serverless team at AWS. And I'm going to be talking about best practices for AWS Lambda. Now, first off, I have to say, I so wish I could be with you there in person in the studio, not just here at home far away. What a cool desk to sit at. I could have sat next to Eric and James and had all the fun, but I'm trying to get over my FOMO. But the talks so far have been awesome today, and I've certainly been learning a lot. Now on to Lambda. Now you may know that Lambda is a serverless compute service that lets you run code without thinking about servers or clusters. Now you can write your code for Lambda functions using the languages you already know and are comfortable using. And development in Lambda is not tightly coupled to AWS, so you can actually port your code in and out of Lambda and AWS. Lambda also runs your code in a secure and isolated execution environment, and this manages the resources required to run your function. Now, one of the superpowers of Lambda that I think of is how it integrates with other services. Over 200 native integrations. And these include things like API Gateway, S3, DynamoDB, Kinesis Streams, Kafka, or even SNS notifications. Now, we launched Lambda more than 8 years ago. And today, more than 1 million customers have built applications that already drive trillions of invokes per month. Lambda is a huge service and continues to grow at a phenomenal rate. Now, we see customers building a huge range of applications with Lambda. They may be doing some web and mobile applications. There's certain plenty of different processing for various kind of things. There's automation, there's machine learning, and you can imagine all sorts of custom integrations that people build. Lambda really is a super versatile service. Now, I haven't got time today to go into all the use cases, but pretty sure Lambda can very likely help you with, a lot of the things you're building. Now, I want to start and go through the Lambda lifecycle, as that sort of sets the scene for going through some of the best practices I'm going to do. But before I actually do, I want to set off a demo to show how Lambda scales and then come back to it, showing it in action. Now, just to set up the demo, Lambda has these great polling capabilities for a number of service integrations. An event source mapping reads items from an event source. It can optionally filter them, it can batch them up, and then sends them onto a Lambda function. The cool thing is we manage these pollers for you as just part of the Lambda service. And that's a big thing. It means you don't have to run and scale your own consumer processors to pull down these messages. And it's actually free. That's a cool thing. You don't pay extra above your function invokes for the service. So I'm going to show how this integration works with SQS, and importantly, how Lambda can scale up to do your workloads. So just switching over to my VS Code terminal. I hope it's not too fuzzy. It should clear quite quickly. Now, I have a producer application written in Node.js, which is just putting items onto the queue. Now, I've actually run this beforehand. It takes a bit of time, and I've basically put 100,000 messages on the queue. So it was very simple. All it's going to do is going to do a message body, and it's going to do the number of the steps and the date and the time. And this is the URL of my queue, and I'm just going to send these messages. So I basically have 100,000 messages sitting on my SQS queue, and I want Lambda to process them. So if I look over here, this is the SQS console, and I have messages available, exactly 100,000 messages available in SQS. So I want my Lambda function to process them. So the integration is already set up. And what is actually cool about Lambda, and we're going to go into concurrency later, is I basically throttled Lambda to say, don't do any processing yet, because I want to show this live on the demo. So what I'm going to do is I'm going to turn Lambda back on, basically, when I'm going to put the unreserved account concurrency. And as soon as I click this, Lambda is going to start processing these 100,000 messages off of the queue. So while that is happening, I'm just going to jump back and I can talk about the rest of the Lambda lifecycle, and then we'll get back to that. So when a request comes in to invoke a function, this is either in the console, via an SDK or service integration, like S3 uploading, an S3 upload triggering a Lambda function, or like with SQS exactly is going on in the background at the moment. So Lambda then checks to see whether the function has been run recently and whether there is actually a warm execution environment. And this is the environment in which your code runs. Now, if there isn't, Lambda needs to go ahead and create one. And it's going to download your code or your container image and then initialize the runtime. It's then going to start to run your code. And this is first the code that is outside the main handler within your function, the initialization code. Now, all the time up to here is what we call the cold start, as Lambda is sort of starting from scratch in effect. Then your invoke is processed, and this is your business logic in your handler, and your handler function runs until it completes, and then can return its response. So this cold start process happens when you scale to process new events or you configure provision concurrency. That's a feature of Lambda which allows you to pre-run this cold start process to improve performance. Now, cold starts always happen when you update your function code or configuration, as this is seen as a new deploy and the function lifecycle starts again. But cold starts can also happen as part of Lambda managing the service for you. Now, periodically, we need to refresh execution environments to keep them fresh and up to date. We also have to replace anything that may have failed. And also, we need to rebalance things across availability zones for better resilience as part of managing the service. Now, typically, cold starts vary from under 100 milliseconds to a few seconds. This depends really on what you're doing in your code. But it's also, you need to think that cold starts only impacts a small percentage of production workloads, typically less than 1%. Now, when you're building and maybe testing your functions, every deploy is a new cold start. So you think that when the scales, the same behavior is going to get crazy when it happens at scale and lots of cold starts. But as you get more requests, you get more available execution environments, more warm starts, and your cold start percentage reduces. And also, cold starts have been significantly reduced when Lambda functions are connected to a VPC. Previously, this did add some latency, no longer. We made a network change a few years ago, so cold starts are no longer an issue for VPC-connected functions. So after this first cold start, that single execution environment is warm. So when another invoke comes in, that it can skip all of that cold start process and just invoke your function handler code. So let's look at that function. And there are these two parts which I've been talking about, the code outside the handler, and this is the initialization code. And this is the part that runs during the cold start, but then doesn't run during the warm start. And this is a good place to set up things like database connections or load dependencies or do sort of anything that future invokes can then reuse. And you can use this to also load other helper functions that your handler can use. And optimizing cold starts is really important for pure performance and boosting up this init phase. Now, mostly for synchronous invokes, but also to reduce costs. You want to make these cold starts as fast as possible. Obviously, the less time your function runs, the cheaper it is. So the idea is to do whatever you can to optimize your cold starts. Then you have the actual handler. And this is the code that runs your business logic during an invoke. It interprets the event. Maybe it's going to write something to a database, read from an API, whatever it is that your custom code is going to do. In the background, my Lambda function at the moment is pulling from SQS. And you also want to make this as fast as possible because it's going to be cheaper. And you also want to reuse what you've already set up in the initialization code. So another tip is separating the business logic, and this is the code you're writing to do your business process, from the actual handler method. And this can make it easier to run unit tests against your code without having to think about the Lambda specific function config. And it also makes your code more portable as you can move your business logic code to other platforms. And also try to minimize your package size and reduce the number of dependencies. This can improve startup performance and also reduce your cost. So instead of maybe loading the whole AWS SDK, if you just need to connect to DynamoDB, just include that specific package instead of everything and use modular SDKs when you can. Now, some languages provide additional options. With TypeScript, you can bundle and tree shake your dependencies. And with Java, you can use simpler dependency injection frameworks, things like maybe Dagger or Juice over maybe more complex ones, such as Spring Framework. And some languages also nicely support ahead-of-time compilation, all to speed things up. Also, think about using the Node version 3 SDK, and this is 3 meg rather than 8 meg for version 2. And this is actually the default for Node 18 Lambda Managed Runtime. Now, you only need to import the packages you actually need, which are now in different modules, and TCP connection reuse is on now by default, which also helps to speed up connections. Now, obviously, it's not a straight switchover, so you do need to do some code work to take advantage of it, and especially this is something to think of when moving to Node 18. Now, it also helps to make your functions modular and single purpose, if you can. Instead of having a single function that runs and does a whole bunch of things, rather have multiple functions that each do a single thing. If you have a single image processing function that maybe changes the format, creates a thumbnail, and adds it to a database, think about maybe having 3 different functions that do each process. This improves performance as you don't have to load extra code you don't need for the bits you're not going to use, and can improve security as each function can be scoped down to only what it needs to do. So what else can you do to optimize your cold starts? There's, of course, the optimizing dependencies, but the big picture is don't load it if you don't need it. This is, of course, optimizing dependencies, but actually everywhere. Avoid loading something you don't need to. That pre-handler code, the initialization code, is great for establishing connections, but also then be prepared to then maybe handle reconnections in further warm invokes. For HTTP connections, use those keep alives in the SDKs. That's now default with the Node v3. And then think how, because the execution environment is reused, you can actually store state for subsequent invokes. But then also make sure you're not storing any state or secrets you don't want subsequent invokes to be able to see. Also, Snapstart, which is recently announced, can help dramatically reduce cold starts for Java. And also, if you need to banish cold starts completely across all languages, you can use provision concurrency. Now, in the Lambda resource model, you choose the amount of memory you want for your function, and then are allocated proportional CPU power and other resources. So an increase in memory size configures an equivalent increase in CPU. Now, it's worth remembering that you pay for the memory allocated to your function, not the amount of memory your function uses. So if you allocate 10 gig to your function and it only uses 3 gig, you are charged for the 10 gig. So it's a good idea to actually test your functions using different memory allocations to work out which is the most beneficial for your function and also what your budget's going to be. Now, depending on the function, you might actually find that a higher memory level may actually cost less because the function can maybe complete much more quickly than at a lower memory configuration because it's got more memory and also because it's got more CPU. So also speaking about architectures, you can actually choose to run your Lambda functions on processors on either x86 or ARM architectures. So Lambda functions can run on Graviton 2, and this is an ARM-based processor architecture, which is built by AWS. And the nice thing is this can deliver up to 34% better price performance compared to functions running on x86 processors. So just going back quickly to that memory thing, working out the optimal memory configuration can be a super manual process if you try all the possible settings yourselves. Now, Lambda Powertuner, this is an open source tool and it helps you to visualize on a chart and fine tune the memory power config to optimize your functions. It actually uses step functions to run multiple versions of your function at different memory allocations that you choose, and it can measure how they perform. And it actually runs in your account performing your real function calls, showing the real cost and the speed, and so you can find the right balance of memory in an automated way. And also you can compare the values of two functions graphically, which is super helpful to compare different functions, maybe before and after when you've done some optimization. And you can even compare when looking at migrating to Graviton 2, as I mentioned, as it's able to compute costs separately for both architectures. So this ARM function, it's 27% faster and 41% cheaper than the x86 version. So this function would be a great choice to move over to Graviton 2. Now, Lambda is a stateless service. So you want to store stateful data outside of the Lambda execution environment. And this can be an external database such as DynamoDB. And this is really great for single millisecond latency and high scale. Or in fact, you can use any other database option. We've got Amazon RDS here and there are database options from our many partners, any external database. And you can store data also in S3. Maybe this is data that doesn't change as often and you don't need high throughput, but you need a lot of scale. And also you can store file data in EFS. This is Amazon's NFS in the cloud. And we've got a customer like Skywatch, and they process large satellite images with low latencies. They can have a whole bunch of Lambda functions pointing at the same EFS mount and process these satellite images in parallel really quickly. Or you can use something like a cache, maybe something like Amazon Elasticache to store your state externally. Now, we talked about VPCs briefly, but a common question we get is whether you need to connect your functions to a VPC. Well, if you have resources in a VPC that your functions need access to, well, Lambda can easily connect to them. Lambda functions still run in the Lambda service VPC and then attach via network interface to your own VPC to then connect to your resources. Now, this setup is on function creation, as I mentioned, so it doesn't impact cold start times. However, you don't actually have to connect your function to a VPC just to make it necessarily more secure, as all internal AWS traffic uses our global backbone and is encrypted, so not just sort of open over the internet. However, if you do want additional network routing control, or maybe egress access control, or more visibility with VPC flow logs, then you can use VPC features for this. And if you do want to use a VPC with Lambda, Lambda really works great with VPCs. So a quick tip for observability. There's lots we could talk about, but I just want to mention this tool, which I'm actually using in my demo in the background at the moment. The open source Lambda Powertools. And this is what the AWS and the community has created. It's all open source, and it allows you to more easily add tracing and logging and metrics to your Lambda functions. And also some of them have some helpful utilities. And this really adds some cool superpowers to your coding. And it's currently available for Python, Java, TypeScript, JavaScript, and .NET. So it's really worth taking a look. And also, as it's open source, you can even contribute and extend the use cases for the help of everybody else. But since we're looking at the Lambda lifecycle, it's worth switching to talk about how Lambda scales with concurrency. So let's switch back over to the demo and see what has been going on. So I have a Lambda function, which I didn't actually talk about before, but this is the code of the Lambda function. And you can see here, I'm basically importing the Powertools libraries, and this allows me to really easily set up that tracing, logging, and metrics. Then this is a simple Lambda function. I am just getting the SQS event from the Lambda function, and I am logging the record body. I'm then sending a metric, which is a successful processing count, and then I'm just going to sleep for 100 milliseconds to pretend that the Lambda function is actually doing something. So if I then head off onto my code, I have some metrics over here. So the Lambda function has been processing all this time. And here you can see I had 100, let's go over there. I had 100,000 messages in my queue, and let's see, 1, 2, 3, 4, say 5 minutes later, I have no messages in my queue. So Lambda has automatically, just by turning it on, gone and just drained this SQS queue of 100,000 messages, with each message taking 100 milliseconds to run. Now, if we also look at how Lambda is going to scale out to do this, this is what concurrency is. And I'm going to cover that shortly as well. So if we can see here, Lambda actually started with 12 Lambda functions running at the same time, bumped up to 39, and then bumped up to 78, and then even up to 81. And then the queue is obviously drained. So Lambda can scale really quickly and really efficiently. If I put 1 million objects on this SQS queue, Lambda would have scaled up even quicker to be able to handle all the processing. Really fast processing. So if I just look now at some of the logging, because this is helpful. This is what the Lambda Powertools does. It's been able to send the message from the SQS queue, which I've logged. It's told me whether it's a cold start. And that was just with one line of in my function code to be able to do this. Then also the metrics. This is the embedded metrics format. Whatever you're doing, use the embedded metrics format. Async metrics from your logs, really super powerful. And this is where it's actually logging that successful processing as a count. And here they all are over there. So these are the logs are being sent to CloudWatch logs. Metrics is automatically sucking up those logs. And I then have my metrics coming from my successful processing. Of course, the demo gods say it's 14,000 messages, not 100,000 messages. To be honest, what I've done is I've just picked the wrong timeline over here. Period of 5 seconds. I probably don't want that. Let's do that over 15 minutes and see what happens. There we go, 101K. So I did run this a little bit beforehand, so that's probably taking that into effect. So that's my custom metric, which the logs have been doing, and it is basically shown what my Lambda function has done. So Lambda concurrency is all about the scaling in action, and I've shown that how it works with SQS. Let's see under the hood how that works. So following the timeline, when a single request comes in for a Lambda function, it's going to run that initialization cold start, and then it's going to invoke your function. Now, and as the function can only handle one request at a time, the execution environment is going to be blocked for this time. Now, if the function is invoked again while a request is still being processed, another execution environment, another instance in effect, is provisioned, and this is going to increase the function's concurrency. Now, when the function code finishes running, it's able to handle another request. And here you can see that request run 1 has completed, which is now warm and free, as we saw earlier. And so this process continues. As subsequent requests come in, it's going to reuse execution environments when they are available and create new execution environments when we need more, increasing the concurrency. So remember back to SQS, when I was looking at the concurrency, it was going up all the way to 81. This is basically the parallel invocation. Lambda has scaled up to be able to handle the load, and those functions were actually taking about 1.5 minutes each to run, and then there would be a warm start, and it would get another batch from SQS and keep on processing. So you can actually count concurrency as the number of parallel requests and invokes that are happening. So for a single execution environment, the number of concurrent requests, it's always going to be 1. But here we can see how it fluctuates as the cold and warm starts happen, and the concurrency is equal to the number of running execution environments. And as we saw before, you can count this in CloudWatch using the concurrent execution metrics, and you can do this for all of your functions or even individual ones. And so how does concurrency actually relate to transactions per second, you may be thinking? Well, the number of transactions Lambda can process per second is the sum of all the invokes for that period, a second. So if a function takes 1 second to run and 10 invokes happen concurrently, well, Lambda is going to create 10 execution environments. So in this case, Lambda processes 10 requests per second. But if the function duration is halved to 500 milliseconds, the Lambda concurrency, it's going to remain 10. 10 execution environments are going to be processing requests. However, they're going to be reused within the second, and so the transactions per second are now going to be 20. So now that I've covered about how Lambda scales, let's talk about not scaling Lambda at all, really. So this tip may be a bit counterintuitive, but yes, of course, there are many occasions when you do need a Lambda function. But what if you could actually remove that Lambda function and have an event source talk directly to a destination and not have to maintain your own code? Well, this is called a direct service integration. And anytime you can remove code, that's a winner in my book. Not having to run a Lambda function if you don't need to is the most efficient way to run your code. So an example I can think of with this is like step functions in two different ways. You can actually remove branching logic from your code and run it in step functions in a managed workflow state machine. So all of those retries and those branching logic, step functions can do that for you. And there's also the awesome AWS SDK integration with step functions. This means you can call any SDK action, and I think that's something like 9 or 10,000 of them by now, directly from step functions without having to use a Lambda function. Now, of course, you can still use Lambda functions in your code to do your custom logic, but they're targeted and they're busy and they do what you need to do. If you don't need to do it, you can just use a native integration. And also intrinsic functions with step functions, there's tiny little Lambda functions to do some JSON manipulation, some maths, or I suppose string operations. Well, now you can do it directly with step functions, reducing code and maintenance using just out-of-the-box functionality when building your workflows. So onto security, we want to make sure that we bake in security best practices into anything we write. It's the easy option to give star permissions to actions and resources to get things working, but we all know it's a really bad practice and something to avoid at all costs. Always use the principle of least privilege when creating IAM roles and policies. Now, to make this a bit easier, because IAM policies can be tough to write, it's always helpful to use a framework. And something like AWS SAM, also the CDK or the serverless framework or Terraform, a whole bunch of frameworks which can actually scope the permissions for you, for your functions, to only the resources used by your application. And AWS SAM policy templates lets you choose from a list of pre-created policy templates to even simplify permissions more. And there's also a new feature of SAM called SAM connectors. And this is another way to manage policies between the source and destination resources. So thanks so much for joining today and being part of Serverless Innovation Day. I really hope I was able to show you some useful tips for using Lambda, and you can really see how flexible and scalable it is. Please get in touch with any questions you have, either via the chat or my contact details here, and enjoy the rest of Serverless Innovation Day. Thanks so much for being here.